Nature does not merely follow paths, but extremizes a physical quantity called action. This fundamental law governs the behavior of every system, from subatomic particles to the expansion of the universe itself. The action is defined as the integral of the Lagrangian over time. The Lagrangian is typically the difference between the kinetic energy and the potential energy of the system. A system with many degrees of freedom is represented as a single point moving through a configuration space. For a particle in 3 dimensions, this space is a 3-dimensional manifold. To analyze paths mathematically, we treat every possible trajectory as a vector in an infinite dimensional space. Each point in this functional space represents an entire function of time. The calculus of variations seeks to find the function that minimizes the action functional. We perturb the path by a small test function to observe how the total action changes. We apply the concept of a functional derivative, which is a generalization of the directional derivative to infinite dimensions. We look for points where the first variation of the action is 0. Setting the variation to 0 leads to the Euler Lagrange equations. These differential equations describe the local physics that must be satisfied at every point along the stationary trajectory. We often work in Banach spaces, which are complete normed vector spaces. This allows us to ensure that the limit of a sequence of paths is still a valid path within our space. Standard continuous functions are often insufficient for proving existence of solutions. We instead use Sobolev spaces, which include functions with weak derivatives that are square integrable over the domain. Hamilton's principle states that the actual motion of a system is always a stationary point of the action. This can be a minimum, a maximum, or a saddle point. Every continuous symmetry of the action corresponds to a conserved quantity. For example, if the action is invariant under time translation, then the total energy of the system is conserved. Invariance under spatial translation leads to the conservation of linear momentum. This link between geometry and physics is one of the most profound insights in modern theoretical science. Rotational invariance in the Lagrangian ensures the conservation of angular momentum. This is why planets maintain stable orbits and why spinning objects resist changes to their orientation. By performing a Legendre transformation, we move from the Lagrangian description in velocity space to the Hamiltonian description in phase space using coordinates and momenta. In phase space, the evolution of the system follows a flow on a symplectic manifold. The principle of least action is here expressed as a property of the symplectic area. Quantum mechanics generalizes this principle through Feynman path integrals. A particle travels along all possible paths simultaneously, and each path contributes a phase factor proportional to its action. In the classical limit, the phases of non-stationary paths interfere destructively and cancel out. Only paths near the stationary action survive, leaving us with the familiar laws of classical motion. Gravity is described by the Einstein-Hilbert action, which is the integral of the scalar curvature over spacetime. Extremizing this functional yields the Einstein field equations. In field theory, we define a Lagrangian density at every point in space. The action is then a 4-dimensional integral over the space and time coordinates of the manifold. The entire standard model of particle physics can be written as a single complex action functional. It includes terms for gauge interactions, Higgs couplings, and fermion kinetic energy. Engineering applications use variational methods to solve structural problems. We discretize the infinite dimensional space into finite elements and minimize the energy functional to find deformations. Robots use the principle of least action to plan energy-efficient movements. By minimizing an action functional that penalizes control effort, they find the smoothest trajectories through cluttered environments. A geodesic is a path of stationary length on a curved surface. This is a geometric interpretation of the principle of least action, where the Lagrangian depends only on the metric. Light follows the path of least time between 2 points. This is a special case of the action principle, where the refractive index determines the local speed of the light wave. While called least action,
It is strictly a stationary action principle. In some cases, like long geodesics on a sphere, the path taken can actually be a local maximum. In functional analysis, we seek weak solutions to variational problems. These solutions might not have derivatives in the classical sense, but satisfy the integral form of the Euler Lagrange equations. The direct method proves existence by taking a minimizing sequence of paths. If the functional is lower semi-continuous and the space is weakly compact, a minimizer must exist. When we add an inner product to our space, we create a Hilbert space. This allows us to use geometric concepts like orthogonality and projections to find optimal paths.
Every functional on our path space can be mapped to an element of the dual space. This duality is critical for modern optimization and control theory in complex engineering systems. In high-energy physics, we vary the connections on fiber bundles. This generalization of the action principle allows us to derive the Yang-Mills equations, which describe fundamental forces. Modern simulations solve the action principle using numerical integrators that preserve the symplectic structure. These variational integrators are much more stable over long periods than standard methods. Finding the global minimum in a complex energy landscape is a major challenge in protein folding and chemistry. The action principle provides the objective function for these optimization tasks.
If the Lagrangian does not depend explicitly on time, the energy is conserved. This is a direct consequence of the stationary action principle combined with the Noether theorem. Gauge invariance is a symmetry under local transformations that do not change the action. This principle necessitates the existence of force-carrying particles, like photons and gluons. The action for a relativistic particle is proportional to the proper time along its world line. Minimizing this action shows that particles follow geodesics in four-dimensional spacetime. In string theory, we extremize the area of a world sheet rather than the length of a world line. This Nanbu-Goto action is the foundation of string dynamics.
Performing integrals over functional spaces is mathematically rigorous only in certain cases, like Wiener measure. This remains a vibrant area of research at the intersection of analysis and physics. The existence of a minimizer depends on the lower semi-continuity of the functional. Without this property, a sequence of paths could head toward a state that is not in our space. The action itself satisfies a partial differential equation called the Hamilton-Jacobi equation. This bridges the gap between particle trajectories and wave-like propagation of the action field. The second variation of the action tells us about the stability of the path. A positive second variation indicates a local minimum and a stable physical state.
The Maupertuis principle is an alternative form of stationary action for conservative systems where energy is fixed. It focuses purely on the geometry of the path in configuration space. By shifting from particles to paths in Hilbert and Banach spaces, functional analysis provides the rigorous language for all of modern physics, from mechanics to quantum field theory. Action functionals change when we zoom out to larger scales. This process, known as renormalization flow, allows us to understand how macroscopic laws emerge from microscopic physics. The principle of least action is even applied in quantitative finance. Agents are modeled as extremizing a utility functional over their possible future wealth trajectories in a stochastic environment.
Variational principles can incorporate constraints such as rolling without slipping. These non-holonomic systems require Lagrange multipliers to be integrated directly into the functional. In some systems, the solution must stay within a bounded region. This leads to variational inequalities, where the derivative is not zero but points back into the allowed space. The principle of stationary action remains the most concise way to express the laws of the universe. It serves as the ultimate bridge between mathematics and physical reality.